Hello, my name is Andy Barkwith and I am a numerical modeller at the British Geological Survey. This presentation will introduce the one-line coastal evolution model, CEM, and explore the physical concepts that define how the model behaves. We'll discuss how the model works, its data needs and outputs. Finally, we'll look at an application to the Holderness coastline to highlight how the model can be used to simulate the evolution of both natural and human-impacted coastlines. Here, we'll examine its suitability for assessing non-local impacts of human intervention on the surrounding coast, and how CEM can be used to assess the sensitivity of a particular location to a changing wave climate. The conceptual model behind CEM makes it best suited to simulating coastlines kilometres to hundreds of kilometres in length over periods lasting years to millennia. It was initially developed to better understand the evolution of sandy coastlines, but has since been updated to include morphological change in rocky coastlines. The one-line approach at the heart of the model means that it's best suited to microtidal environments where waves dominate sediment transport processes. The dynamic evolution of wave-dominated stretches of open coastline are shaped by transitioning periods of diffusion, which smooth coastal form, and anti-diffusion, which acts to grow or maintain any shoreline perturbations. Whether a section of coastline is in a state of diffusion or anti-diffusion is highly dependent on its relative angle to breaking waves, which create gradients in a longshore sediment transport. To capture the impact of these states, the CEM uses linear wave theory to transform waves from deep, offshore locations to the shore face, where they provide energy to push sediment alongshore. The net change in sediment volume at any particular location determines the shoreline position, and therefore whether it is eroding or accreting. As with most numerical models, initial setup and process representation play a part in influencing the simulated evolution of a coastline. By reducing the influence of the model setup, we are able to place more confidence in the results. Within the CEM, there are multiple processes represented, each having a primary role. However, each also comes with caveats and assumptions that can heavily influence a simulation. The model domain represents a plan view with positions defined using alongshore and cross-shore coordinates. The domain is discretized into square cells of a set width. Each cell is able to be occupied either singularly or by fraction of land, sand, or water. The shoreline consists of a line of cells between the land or sand cells and water cells. On open ocean coasts, a cell size in the order of 100 metres gives reasonable results with the tide step of a day. Locust stream, back barrier, or other low-energy wave environments may require a smaller representative cell size and an adjustment of the time step. Typically, the fractional value within a cell represents the cross-shore extension of the subaerial shore. Depending on requirements, a number of differing boundary conditions may be used within the CEM. Under a periodic boundary, sediment passing off one domain edge returns on the other. This setup essentially represents an infinitely long sandy coastline and is useful for exploratory modelling, such as in the investigation of feature self-organisation. For simulations representing real coastlines, sediment addition and removal at fixed points can be used to characterise natural or man-made boundaries such as estuaries or ports. CEM transforms waves using linear wave theory across shore-parallel bathymetric contours that extend seawards to the depth of the shore face. This simplification provides a fast calculation of the breaking wave height and angle, which are used to drive a longshore sediment transport. However, it inherently excludes alongshore wave energy convergence or divergence, ignores wave transformation over the shelf, and is not well suited to coastlines with a complex bathymetry. As a shoreline protuberance, such as a spit or cusp, extends seawards, it can shadow other parts of the shoreline from oncoming waves. Within the model, a line-of-sight search is performed for each cell in the direction of wave approach to determine if any of the shoreline will block approaching waves. If a part of the shore interferes with the cell's line of sight, it shadows the cells from the dominant waves. This simplified linear search neglects the effects of the relatively small amount of wave energy that could refract or diffract into shadowed regions. As one of the underlying model assumptions holds, that protuberances are large compared to the shore face, wave refraction should occur close to the shore and this effect will be minimal. This approach also means that the model neglects the possibility for wind generation of waves within a shadowed region. Sediment transport for each shoreline cell is determined across its downdrift boundary. Breaking wave height and angle are inserted into a sediment transport equation to determine the volume of sediment to move across the boundary. Various sediment transport equations can be used within the CEM model. However, the default is the Komar formula, which relates volumetric alongshore sediment transport to the breaking wave height and angle. The empirical constant K, which relates the driving forces to volumetric sediment flux, can be modified to represent different grain densities and sizes. For example, a value of 0.4 is representative of a typical quartz density sand. Within the model, a cliff line behind the shore face allows the influences of geology to be included, albeit in a simplified manner. The cliff line simultaneously provides a resistance to erosion and a source for the shore face sediment as the cliff line retreats. The fractional value of each shoreline cell is updated using the net difference between sediment influxes from and outfluxes to surrounding cells. If a cell becomes full, an adjacent cell in the offshore direction will begin to receive sediment and becomes the new active coastline cell. If a cell becomes empty, the model steps away from the shore face and the cell behind takes over as the active coastline cell. Man-made structures and other influences can be represented in a number of ways. Hard structures, such as sea walls, may be represented by setting the erosion potential of a particular cliff section to 0 meters a year. Beach nourishment can also be represented by introducing material at a particular location, either continuously throughout the simulation or during discrete events. Other structures are more difficult to represent, particularly those that impact sediment transport at the subcell scale, such as groins. CEM can be run using a set of internal configuration parameters and without the need for external files. However, this functionality is limited to highly abstracted simulations and not easily implemented for simulation of any real coastlines. To overcome this, the model was modified to ingest gridded files representing properties that change spatially, and a time series of deep water wave climates. The internal approach to wave generation uses a simple full bind method. Otherwise, a text file containing a time series of wave data is required. This file consists of wave approach angles, heights, and periods that are used during the model run. Coast and cliff lines are computed from a gridded file containing fractions of land, sand, or water input as a gridded ASCII file. To save setup time, there is an option to initialize using an internally generated smooth shoreline for more abstract simulations. The CEM has been designed to permit initialization from previous outputs, allowing discrete changes in the model to be introduced manually. Many of the model parameters are specified within the model code itself. These include discretization settings, the position of sediment sinks and sources, cliff properties, and overwash characteristics. Model output consists of snapshots of the coastline during its evolution. CEM can be configured to write the resulting coastline at any point during the simulation. The output format of the coastline file is the same as the gridded ASCII input files. This file convention is compatible with several software tools for plot generation, such as MATLAB, Python, or GIS. CEM has been applied to numerous coastlines worldwide. The Holderness coastline on the east coast of the UK is one of the fastest eroding coastlines in Europe. It is formed of long stretches of beach backed by boulder till cliffs and a well-defined chalk headland at its northern boundary. There have been multiple efforts to protect this coastline from erosion, but these are now limited mainly to sea walls fronting towns, villages, and major infrastructure. We were interested in understanding how sensitive this coastline is to changes in wave climate, and if sea walls impart a non-local impact on the morphological evolution of the coastline. The CEM setup for Holderness was defined using a mixture of observed values and, where less informed, an exploration of the input parameter space using a Monte Carlo method. The model was calibrated against observed coastal erosion rates over a 15-year period using deep water information recorded from a buoy. The model setup that gave the closest match to the observed erosion rates was then used for assessing the sensitivity to potential future change up to the year 2100. By running an ensemble of hundreds of different wave climates through the model, erosion was found to be most sensitive to changes in wave direction, rather than height or period. The northern parts of the model were found to be particularly sensitive to change due to their orientation, shadowing from the headland, and the lack of protection from beaches. Most surprisingly, the model showed that for the majority of scenarios erosion is reduced in the future as wave angles move away from the erosion sweet spot of 45 degrees. The introduction of sea walls were found to modify the response of the coastline to changes in wave climates, particularly in southern sections of the coast where there is more beach sediment available. Under certain wave conditions, and after decades of erosion in the surrounding areas, seawall structures were found to interact with each other, trapping sediment over long distances. The coastline evolution model is based on a one-line approach and is best suited to simulating sandy, microtidal coastlines kilometres to 100 kilometres of length over periods lasting years to millennia. It can be used for either highly abstracted modelling or to explore the evolution of real coastlines. A simple linear bathymetry is assumed by the wave transformation method, and therefore care must be taken in interpreting the results where a complex bathymetry exists. Sediment transport is limited to one fraction, the properties of which can be changed by modifying the transport algorithm. CEM allows initialization and forcing parameters to be set internally. However, these are limited to only simple parameterizations. Complex coastlines and observed wave climates can be introduced through external ASCII gridded files. The model output requires the use of external software for construction of images or videos. The structure of CEM allows a relatively fast simulation, which lends itself to exploring uncertainty or the sensitivity of a system through Monte Carlo or ensemble methods. This makes CEM particularly useful to stakeholders interested in understanding and quantifying the potential impact of future change on the surrounding coastline. For further information on the coastline evolution model and the ensemble approaches used in this presentation, please see the following research papers for reference.